Okay. Hello to everybody. Welcome. Good morning. I am Danilo Coll from NGSoft, and I am proud to present the webinar Design for the Real World, held by Dr. Timothy Hunter, who is the founder and the president of the Wolf Star Technologies. The webinar will last approximately 30 minutes and will introduce you to a new vision of design between simulation and experimentation. Tim will explain you how to develop the right load cases acting on your structure and how to design for the real world using the real load case. So I leave the. Okay, Tim, you can start with your presentation.
Thank you, Danilo.
Okay, you're welcome. Thank you.
All right. And I will share my screen somehow. Hold on.
Okay. Lower
share screen one. Here we go.
Okay.
All right.
Okay, that's fine.
Okay. All right. Well, thank you, Danilo, for introducing me here. So I've got a kind of presentation about talking about TrueLoad and ANSYS and really FEA in general and designing for the real world. So this is about understanding the loads in your structures and tools that we've got to help you understand those loads. So just getting right into it here, a little bit about me. So we founded Wolf Star Technologies back in 2010. So we've been around for 14 years now. And prior to that, I was 22 years of doing product development at Harley-Davidson. I was chief engineer of vehicle structures. And I've done everything from structural analysis to working with manufacturing and test. And I understand what all you folks go through trying to develop product. It's a challenge out there when you're trying to develop product. So I fully understand where you're coming from there. And some of the accomplishments in my career here is while I was at Harley-Davidson, I developed a topology optimization methodology that we were using internally at Harley for a long time. And this came out just about the same time that OptiStruct came out from HyperWorks. And then when I was working on my PhD dissertation, I developed an FEA-based fatigue methodology for metal fatigue, and I also developed an energy-based fatigue modulus. And that my dissertation was launched just about the same time as FE-Safe came out. And then while I was at Harley-Davidson, I also developed the TrueLoad load reconstruction methodology. And I thought, you know what? I better take this to market so we've got something good that we can share with everybody else. So I wanted to beat everybody else to the market with this. So that's what we did. Our tool set at Wolf Star Technologies, we use basically every FEA tool out there, from FEMAP to Abacus to Siemens SimCenter and Nastran and ANSYS. Okay, so we use all the tools. We've got good experience with them. For doing durability work, we primarily use FE-Safe, but we've also have developed internally what we call TFU fatigue, which is a signal-based fatigue analysis tool, and is more or less a derivative of my dissertation. And then, of course, we've got our TrueLoad suite of softwares. So, and since we've launched our company, we have had great development partners. We've had Dassault Systems, ANSYS, MSC, which is now Hexagon, and Siemens. And we've got this really strong development partner in CE-Tron. They provide the API for our software, lets us to do the visualization and reading of everybody's databases. So we've got a really nice foundation here for our company. So just getting into the products from Wolf Star Technologies. So our flagship product is a product we call TrueLoad. It basically turns components into load transducers. We have the users set up on their FEA models a series of unit load cases. We look at the strain results from those unit load cases. We identify places to place strain gauges on the structure. And then we extract a correlation matrix that relates strain response to the unit loads. And then once we've got that, then we have our customers place physical strain gauges on the physical parts. And then we take those physical strain measurements and multiply them back by that correlation matrix to back calculate the loads. Okay. We're essentially turning any part into a load transducer, and we're leveraging the FEA model to do that. So that's what we're doing with TrueLoad. Okay. A second tool that we've got in our suite of products is called TrueQSE. QSE stands for quasi-static events. And this basically will linearly superimpose the results from your FEA model via user-defined functions. And that by itself is great. But what happens when we're using TrueLoad, you're going to get time histories of loading functions that map back to the results in your FEA model. And then TrueQSE becomes a way that you can back expand those results and basically get stress strain displacement plots for any node or element in the model, and even generate operating deflection shapes. So it's so powerful for you understanding your results. We bundle the TrueQSE package with TrueLoad whenever you buy TrueLoad, because you really need to have TrueQSE to understand the loads that you just measured. And a third product we've got here, this is an analysis only tool, and we call it TrueLDE. And LDE stands for linear dynamic events. And this is basically a post processor for your linear dynamics solutions in your software. So in the ANSYS code, it's called MSUP, modal superposition. In Abacus, it's called star modal dynamics. So it's called different things in different codes. But what happens is that these post processors in the FEA's codes, they're really not designed to handle time varying or frequency varying results. And this is really tuned to work around that domain. And we've got some very powerful attributes to our software. When you set up your linear dynamic solves to work with our software, we end up saving you 90% in your computational time. So just using our software, you just bought yourself a supercomputer. And then we've got really strong features. Some of them, for example, we can convert your results between time domain, frequency domain, and PSD domain and back and forth. So we've got to give you very, very powerful tools to understand and look at your results. So all of our softwares are really concerned about making sure you've got the loading right, and you need loads in order to do FEA-based fatigue. So what we've naturally have got is we've got natural interfaces to the major FEA-based fatigue packages out there. So if you've got an FEA fatigue software, it's really just one button click to go from the loads in our environment into your FEA-based fatigue software. So it makes using your FEA-based fatigue software much easier, okay, and much more efficient. So, what's the ANSYS users or any FEA user's biggest challenge? Well, frankly, it's what's the load. So if you're an engineer that's got to design product for this motorcycle, and the loads are crazy nonlinear, you can't measure them, you can't simulate them, but you as an engineer are responsible for designing parts that function and are durable. Well, what do? Well, we recognize that all of the subsystems are basically responding linearly. So we're going to put strain gauges on, the swing arm, the crankcase, the frame, the handlebars, the fenders, the fuel system, the luggage system. We'll put strain gauges on all these subsystems, turn these subsystems into their own load transducers, and then we can use those loads to do design and optimization on the structure, okay? So we really solve this really challenging problem of understanding the loads by leveraging the linear response of the subsystems. So this is a first to market solution. It's based on a technology called influence coefficients. And influence coefficients have been around for 50, 60 years. But the problem with influence coefficients historically has been it was all done experimentally. So people would guess where to place strain gauges. They would go through very elaborate structures lab tests to put the unit loads on their parts in the lab, and then they'd end up not having a good correlation matrix. And then they go to the field and they measure the strains, and the loads wouldn't make any sense. And that's just because they didn't know where to place the strain gauges. And what we're doing is we're leveraging the FEA model and scripting to make sure that we get the optimal strain gauge placements and the best correlation matrix we can get. Okay, this is what we're doing. All right. So historical approaches for people to understand loads are to use things like these load transducers like you see on the screen here. And these are perfectly fine devices. You know, these are very good products for measuring load. The problem is that when you want to use these on your product, well, now you've got to remove material to insert the load transducer. So now you've just changed the mass, you just changed the stiffness. You're measuring something, it may or may not be the actual load. And then to add insult to injury, now when you bring those loads back to the structural analyst is typically working on the as designed part, and they've got to rework their FEA model to look like your test part in order to use the loads you just measured. So it's not great, but this is traditionally what companies have been forced to do to try to measure loads. Another approach that people try to use is strain gauges. So typically what will happen is the analysts will look at the FEA model and come up with some strain gauge locations. They might talk to their colleagues and come up with some more. And they come up with maybe, 30 channels of strain data. And they say, here, let's lay these strain gauges on and go measure them. And then when they get that strain data back from the FEA model, from the proving grounds, they just scratch their heads because the loading is so complex in the real world versus their FEA model, nothing matches. So typically what will happen is you'll pick one or two channels of data at one or two points in time, and you'll work for days, if not weeks, to try to get just those two strain gauges to light up qualitatively the same way, not even quantitatively, qualitatively the same way. And you say, that's my load case, and then you use that load to do redesign. And then the next time you get to the proving grounds, you've got the same problem or even a new problem, and you repeat this cycle over and again. Okay. This is just the, something that structural analysts go through all the time. I have done this several times myself. It's just very frustrating. Here you're trying to use all the right tools and you can't get the right answers. So this is not what we want to do. Okay. This is just wasting time. All right. So we've got to, and what's wrong with it? What's going on, right? We got great FEA software, we got great analysts, we're doing the right stuff by testing, and we're even using tools for doing fatigue analysis off the FEA model. Our company has made all of the right investments, but we're not getting the right answers. Well, what's going on? Well, the problem, quite frankly, is you got too many variables, right? You got the gauge locations, you got the load cases, and the quantity of data. So if we had gone to the field and with our 30 strain gauges and come back from the proving ground, we'd have a time history of data that might be 500,000 data points long. And the problem is at every point in time for those 500,000 data points, for those 30 strain gauges, you've got a unique loading recipe for each point in time. So if you've got 500,000 data points, now you got 500,000 loading recipes, and you just can't do that manually. So it's just a hard problem, and we're kind of left in this kind of no-win position here. Okay. So the solution here is quite simply TrueLoad. TrueLoad is doing what's called in situ load measurement. So in situ load measurement is going to turn complex components into multi-channel load cells. And we get to leverage the FEA model to work with the test data. And we work with all FEA. We've got really nice plugins for ANSYS Workbench and Abacus CAE. But at the end of the day, we can work with any of your FEA data. It doesn't matter what platform it comes from. And then at the end, and then when we use TrueLoad, we're going to get optimal placement of strain gauges. And then from these optimal placement of strain gauges, we're going to get strain correlated loading. So this is fantastic. Now we know that our loads are right because they're actually matching these strains that we've measured in the field. And now that we've got strain correlated loading, if you're going to use FEA-based fatigue, this is the best thing to use because now you've got strain correlated loading that you can drive your FEA-based fatigue software with. Okay, so this is what we need. So here's a workflow. This is how it all looks. So we start off doing this process with your FEA model. So this is your normal FEA model. And then what we're going to do now is have you put on unit load cases on this thing. So we're going to not put on a complex loading environment. We're going to take your complex loading and break it down to the component loads. So it might be 1 kilonewton in the X direction, 1 kilonewton in the Y direction, 1 kilonewton in the Z direction, maybe a pressure load, maybe a thermal load, maybe an inertial load. But this is you thinking about how does load come into your structure and you're applying unit loads at those locations. Once you do that, you solve that for all the results there on those unit load cases. And then you launch the TrueLoad pretest software. The pretest software is going to look at all the strain results for all of those unit load cases and then come up with the optimal strain gauge placement for you. Okay. And we'll show you the optimal strain gauge placement. And then we've got tools in the software that allows you to reposition and reorganize where the strain gauges are laid. You want to make sure you're not, you want to make sure gauges are kind of parallel and perpendicular edges. You want to make sure they're not being blocked by their shielding and things like that. So we're going to give you tools to move the gauges around. But at the end of the day, then we're going to extract a correlation matrix that relates strain response to the loads on your structure. So that correlation matrix, we're going to store that to disk, and they'll take this information about the gauge placement in 3D space and bring it back to your actual part in the lab. And then you work with your test team, and you'll instrument up the parts, and you put strain gauges on the parts. And now in the measurement environment, we just need to get time histories of strain. So you could do testing in the lab, you could do testing in your proving grounds, you could do testing in your customer's hands. We just need to get a time history of strain data on your part. And once we've got that, then we bring that into the post-test software. And the post-test software now is going to take the measured strain data here, multiply it by the correlation matrix from pretest, and that will generate for us time histories of loads. Okay. Now we've got loads. Okay. Loads are loads are loads. We could bring those back to your FEA model using manual means, but I highly, highly recommend you leverage the true QSE files that get generated automatically with TrueLoad. And the true QSE files are going to manage all unit load cases and the corresponding loading functions automatically. And this is where we can query any node and element on the structure for any response, generate operating deflection shapes, and we can then take a look at the response and maybe do some iteration. Okay. And then once we've got that, then now that we've got these strain correlated loads, now we can go into our fatigue-based, FEA-based fatigue tools, because your FEA-based fatigue tools are bringing a couple things for you, right? They will have a database of fatigue materials. They will have an access to your FEA code, and then they'll have a durability calculation engine that's proprietary to them. And then, so this is what they're doing. But in order to drive all this, they need to have a duty cycle. And now we've got strain correlated duty cycles. So we've got the best possible duty cycles to drive our FEA-based fatigue tools. Okay. So this makes it super powerful. So this is the flow chart. I know it looks a little bit complicated, but really the first 4 blocks are you turning your part into a load transducer, and the bottom flow chart is using design and optimization once you've got the loads. So typically my customers will do the first 4 blocks once and the bottom flow chart 20, 30 times as they work on optimizing their parts. Okay. So how does this stuff work? Okay. Well, it's all based on linear systems and loads. Okay. So a linear system is described by where loads are proportional displacements, displacements are proportional strains, strains are proportional loads. That's a linear system. Okay. We fully realize everything in life is nonlinear. Okay, we get it. Everything is nonlinear. But what we're doing is we're turning your part into a load transducer. So we're going to target nominal areas on your part where the strain response remains linear and proportional to the exterior loads. We're going to stay away from high strain gradient areas like welds or bolted joints or areas of contact. We're going to be in nice nominal areas where the strain responses are remaining linear and nominal to the exterior, linear and proportional to the exterior loads. The loading can be as nonlinear as anything. Okay, it could be ramp loading, sinusoidal loading, even impact loading. That's okay. We just need that strain response to remain linear and proportional to exterior loads. So I'm going to take this little diagram here and turn it into a couple of equations, okay? These are going to be the only equations in the whole presentation, okay? So I'm going to turn it into a couple of equations here. So the right-hand side, well, that's F equals Kx. That's Hooke's law. So if your structure is obeying Hooke's law on bulk, then the left-hand side of the triangle has got to work for you then, which is strain times a correlation matrix is equal to load. And we're going to calculate loads as being strains from test times a correlation matrix from FEA. This is what we're doing here, okay? This is what's known as influence coefficients if you look it up in the literature. All right? Okay. So we've got customers in all of these product segments. So if your product is experiencing loading from the land, wind, sea, air, from your customers directly, or even internal loading, we can back calculate those loads and give you powerful tools to do analysis properly. So here's a V diagram in product development. We've all seen this, where we go from the voice of the customer, we get product requirements, we start working on design, and then coming up the other side of the V where we start going into physical tests of doing component, subsystem, system tests, functional, and then acceptance tests, and launching the products. Okay, this is the typical V diagram. We all know this, and this is where ANSYS has got its strong suit here, which allows us to do all this iteration in the virtual world here. And what we're going to do now is we're going to deploy TrueLoad to leverage the physical test and bring knowledge from the physical test back into the virtual world so that we can understand the real world better and drive better simulations in the virtual world. So TrueLoad is all about taking information from your physical tests that you're going to do anyways, bring it back to the virtual design world so that you can get stronger and better as you go forward. And this way, we can eliminate one or more design build test cycles. Because the problem that people have in doing product development is something will fail in the physical world, and then they scratch their head to say, well, why did that fail? And then they iterate and try to guess at what the loads are in the design world, and they waste less time, and they start it again, and they go back and forth and back and forth. I have seen my customers, and I have done this personally, where I have eliminated one or more. In fact, I've eliminated half or more of the design build test cycles in product development. Okay, I have done it personally myself, and I see my customers do it. So, and just to show you how this looks like in the ANSYS Workbench environment. So on the left here, we've got a standard static structural block here. And then all we have to do is we can bring in the pretest component, attach it to our structural analysis there. And this is where we can go in and define our strain gauge placement in TrueLoad pretest. And then once we've done that, we go to our proving grounds, we collect a bunch of strain data. In this example here, I've got 3 sets of tests that we've done, and then we can hook up the post-test component to our pre-test component and bring in our test data, our strain data here, and we can generate the loading then from our tests. And then once we've got those loads, then we can then hook up our quasi-static true QSE components to our loads, and then we can go and explore the response of our structures based on those loadings we calculated. So the really nice thing about the Workbench plugin for ANSYS here is that now all of these files we're generating for TrueLoad, they all become part of your Workbench project folder. And so they get stored in your Workbench project folder. So that basically it all looks the same to you as an ANSYS user. Everything's stored in your Workbench project folder. So everything you need is there, right there in your Workbench project. So if we take a look at these 3 events that we've got here, these 3 quasi-static events, let's say we wanted to do a durability analysis and say, let's say, hey, we want 3 repeats of the first, 5 repeats of the second, and 10 repeats of the third. We can bring that to our duty cycle manager that will mix those together. And once you're happy with what that duty cycle looks like, then it will dump that out to your fatigue software so you can do a complex multi-event durability cycle in your fatigue software. All right, so this is what the Workbench product looks like. It's a very nice way of using TrueLoad, and it just works a little seamlessly with you in your ANSYS Workbench environment. So I've got a series of examples here. This one here is from Terex, and Terex is a company that makes these sliding booms. So so this was a very interesting application for them, is because they've got a situation with these sliding booms because the boom is sliding in and out of the crane here, and the load is moving along the length of the boom here. And so this was a very special application for us here, where we basically implemented our moving loads technology, so we can have the loads move along the length of this. So you look at this FEA response. This is a highly nonlinear FEA response, but everything going into the FEA, into the TrueLoad analysis, is linear. So and when you think about doing a nonlinear analysis in FEA, what happens in a nonlinear analysis in FEA is as you're going along your material curve nonlinearly, your analysis tool is doing a piecewise linear solution. and then it brings in the new materials, and then it does another piecewise linear solution. So it does a series of piecewise linear solutions until the solution converges. Well, TrueLoad is just doing that technique just differently, okay? We're doing a bunch of linear analyses on the front end, and then we're letting the strain gauges drive the solution here. And so that's why we get this highly nonlinear result with a all linear solution with all linear analysis going in. And so I'm showing a couple things on the bottom of the plots here. On the bottom left here, I'm showing the measured strain and the simulated strains here. So the blue curves here are simulated, and the green curves are measured, and so you can't see because they're all laying on top of each other. So I did a nice little cross plot here right next to it of measured strain versus simulated strain, and you can see I've got near 1-to-1 correlation there. Okay, I'm getting perfect correlation on this very complex thing. There's 50 strain gauges in this example. So we had a lot of strain gauges laid on this thing. And what's really neat here, you're seeing this animation. And on the top of the screen here, I'm highlighting the regime that I'm actually animating here. And you see, and this is basically the loading profiles. And you can see on these loading profiles here, I've got these huge spikes of loads. These huge spikes of loads are unrealistic. Okay, these are unrealistic loads going on here. And what's happening is I was frustrated. I couldn't understand why I'm getting these huge loads because I'm getting this perfect strain correlation. So I know the strain correlation is good. So I couldn't quite figure out what's going on. And through a lot of work working with my customer here, I found out that at certain locations, at certain configurations of this crane, the crane is passing through a buckling mode. So what's happening is that we're passing through this buckling mode, we're getting a spike in the strain response. And since we only got linear load cases to work with here, is basically leveraging those linear load cases and making sure that it can match the strains and those buckling things. These loads aren't real. These are buckling loads going on here. And so what was very interesting for this customer is that they've always seen this in their test data and they've never understood what was going on. And through this TrueLoad analysis and through some extra work we did, we were able to identify that they've got buckling configurations going on here. And so now they've actually added to their design guide how to design the sections and the extensions to make sure that they never pass through buckling. So this is a huge design insight to them that they couldn't have gotten without TrueLoad. Okay. So here's another example. This is Cummins. Cummins is a great user of ours, and they use it on a lot of applications. But one of the big applications they're using it is on their frames for their gen sets. And these gen sets are huge. They're about the size of a railroad car, and they have never been able to get good strain correlation and understand the dynamic responses of these frames until we came along. And they're a huge user of TrueLoad. They're using it constantly to understand their work. And here's another one. This is Kubota. They're a relatively new customer of ours, and Kubota is having us take a look at their tractors that they've got and looking at the tractor and also the loader arms and doing a full complete thing. So you can see here's an operating down on the right hand side. That's an operating deflection shape that we've calculated from the strain response that they've measured. So this is just another nice application for a TrueLoad. And this is a great example here. This one is from our customer Aaron's. They make these zero turning radius lawnmowers, and they came and talked to us originally on this product here. They basically they've got these engine decks here, and these engine decks were working just fine, but their transmission supplier was saying that their transmissions were getting too hot and they needed to find some way to put holes in there. And so they hired us to come in and help them out with this whole procedure. And they had started down the path themselves initially, and it didn't work. But basically, with our TrueLoad software, we were able to come in and say, "Hey, lay these 8 strain gauges here on your structure," and then on the left here, you can see the time histories of strains and simulated strains in the background. And here's one of our standard cross plots. We're plotting measured strain versus simulated strain for all of the strain gauges for all time on the plot. And we've got this nice 1-to-1 strain correlation here. You know, this is one of the things that customers get. And now that we've got these strain correlations and these great loadings, they were able to then drive their durability analysis. So I've got a plot here showing their fatigue material. So yellow is your goal of 10,000 hours here. So yellow is the goal here. And so we want to look for yellow, green, and blue on these plots. So basically, their baseline is here, which was just fine. There's some red here because of the RBE on the structure. But then this was their initial design they did on their own, and they failed right through this location in like 1,000 hours. And that's where the fatigue software is predicting that as well. And then you can see the various iterations we did with TrueLoad to come up with a better design. We did this whole project from beginning to end in 8 days, okay? And when we talked to the engineers, if they did this without TrueLoad, it would have taken them 30 weeks and 6 design iterations. They would have spent, upwards of $150,000. And with our project, they spent under $1,000. Okay. This is typical of our customers, what they get, the type of value they get out of this. All right. So basically the TrueLoad applications, we can work on mechanical products of any size in any domain. So if you've got parts that are experiencing strain, we can help you back calculate the loads. So, I've got on here a can crusher that I use for an example to a razor scooter, to airplane wings and front end loaders and mine cars and even tanks. These are all projects we've done. Okay. And the market for TrueLoad is pretty much the broad breadth of mechanical product, from aerospace and defense, automotive and transportation, industrial machinery, heavy equipment, marine. And you can see these are our customers on the screen here who are using our product. All right. That kind of gets me to the end here, Danilo. I'm all done. And thank you very much. I don't know if we've got any questions or anything, but I'm happy to answer any questions if you got them.
Okay, thank you very much, Tim. And if there are some questions, I don't know.